Hello students, in this video we'll discuss the Riemann-Christoffel tensor. Let's be given a covariant vector AJ and consider this quantity over here. I'm going to do a covariant derivative in P, a covariant derivative in N, minus a covariant derivative in first N, covariant derivative in P. On a manifold, they don't commute, right, of AJ. And let's see what this quantity gives us over here, okay? So let's focus in on this quantity over here, then we'll symmetrize against it, right? So if I have covariant derivative P of covariant derivative NAJ, that's a two covariant thing, right? So what will this be? This is going to be d by dx P for the P derivative of this thing over here, of this expression, covariant derivative AJ. And then I have what? Since it's covariant, I'm going to have two quantities over here. I'm going to need to trace over two quantities over here of a gamma, of an L, and I'll have a P and a J, and then I'm tracing over L now, right? So I've used P and I've used J, so I have to hit the N over here, right? So I'm going to have a gamma N, a L. That gives me one of the components. Let's make sure I have the right order. I'm tracing over L, and I have a J and N and a P, J and N and a P in the right order. Good. Then I do a gamma L. And now I'm going to trace over the N over here, right? So I'm going to put I have a P and a J now. I have a P, I have a traced over J. So now I'm tracing over L, now I'm tracing over N. So that the J is over there. So now I have the N over here, right? So now I have a P and then an N, P and then N. And then a delta L of AJ, delta L of AJ. Okay? And so of course these again have the right order. I have an N, a J, and a P on the bottom over here. Great. Now one more intermediate step over here is I'm going to differentiate this thing over here. So of course, what is this thing? This of course, give us a little bit more room. Intermediary, so this thing over here, so just let's note that the N derivative of AJ is d by dAJ dx N. And then I have a minus gamma. I'm tracing over the J now, right? So I have an N in the bottom and a J in the bottom, and the bottom, J in the bottom. Let's put an A on top over here, and then A sub A like that. Okay, that will give me that covariant derivative over there. And maybe we'll change that A to an L just for simplicity's sake to keep all my indices the same. Doesn't matter what you use for that index over there. Let's turn that into an L instead of using L everywhere else. All right, so let's turn that into an L and an L. Great. All right, that's the covariant derivative. So now I'm going to do the derivative of this thing over here, right? So now if one more intermediate step, this expression over here is equal to the xp derivative of this thing over here. So that's going to be two terms. It's going to be d squared aj, and then I have an xp derivative of an xn derivative, xp derivative of an xn derivative, like that. That's the first term. I do the product rule over here, then I'm a minus the p derivative. So I have a p derivative over here, a p derivative of gamma lnj, and that's hit with al. And then a minus gamma, of course the derivative over there, right? And then gamma of NJL, and then the p derivative of AL, then A, L, L, X, P, like that, okay? That's the derivative over here of this thing over here. Now these two terms that straggle along, gamma of P, J, L, gamma N, A, L, minus gamma L, P, N, gamma L, A, J. Great. So that's what we get when we do the P covariant derivative of the nth covariant derivative of AJ. We get this expression over here. Now I'm going to symmetrize this, and I'm going to replace every n with a P and every P with an n. So if I do gamma n, gamma P of AJ, which is the other term we're going to subtract off, what are we going to have over here? We're going to have the same sort of terms. We're going to have partial squared A, J, partial n, partial P, okay? Then I have a minus partial xn, gamma L, pj, gamma AL, like that, because I've changed all the n's to p's, right? And then minus gamma L, there's an n, so that turns into a p, j, partial AL, partial xn, minus gamma L, n, j, gamma p, A, L, and then minus, you get funny anagrams as you do these things in Riemannian geometry. You can figure out how you can spell your favorite word, and if you have a tensor of that order, you can try to put those words into a paper and see if the referee flags it. It's a fun exercise. Okay. Like for example, I wrote a paper on SKLC, scalar metrics, which is see if you can find some funny words in that paper. Okay. All right, good. And then I have this last term over here, which is, I'm going to place the p's in the end, but nothing changes over there, right, because of the symmetry, right? So remember this is gamma of L, so I've changed them over here, right? But now, so I have this term over here, then 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 this term over here is finally going to be an NP gradient L, A, J, like that. Now, if we subtract these equations, some terms are trivially going to cancel out. Look at this term over here and this term over here. Those terms are exactly the same. So when we subtract, those terms are not going to appear. Look at this covariant derivative over here and this covariant derivative over here. By the what? By the symmetry of the Christoffel symbols, when I subtract those are going to cancel out. Great. So now what are the terms that are going to remain over here? So these other terms that are going to persist over here. So let's figure these out. So these terms over here are going to be the negative terms over here, right? And so what are we going to have? So we're going to have a, let's look at these terms over here first. I'm going to put those terms over here, those are positive, and these terms over here are negative, right? So I'm going to have a d by dxn of gamma L P J A L, and then I have a minus d by dxp of gamma L N J A L, like that. So I've taken care of those two terms. And then what terms do we have over here? So we have these terms over here, okay? And then we have these terms over here. So let's look at these terms over here carefully. And these terms over here, right? So we can expand those terms out a little bit more. So let's do that next. So we're going to have these gamma, so I have minus gamma L N J partial AL partial XP. And then these terms over here are positive. So these terms are going to be positive gamma L P J partial AL partial XN. Then I'm going to do minus gamma L P J. And then we're going to hit this with a what? With a partial AL partial XN. XN. And then minus gamma of what? Minus gamma of NL, NL, and then I have to put an A up top here, and then an A sub A, okay? And there's one more term over here. These terms are over here going to get a plus, right? So then plus gamma of NJL, and then a P derivative, this thing, so partial AL partial XP, okay? And then a minus what? Minus gamma of what? So gamma of PL, and put an A on top over here, and then an A, then an A sub little a, like that. Right. Okay. So those are the terms that we're going to collect over here. Now let's notice the partial derivative terms should cancel out. So let's look at this term over here. This is a minus gamma LNJ, and over here I have a plus gamma LNJ ALIP. So this term over here and this term over here are going to cancel out with one another. Now let's look at this term over here. The next term we have over here, which is going to cancel out, is this term over here, right? So that term over there, that is going to be a gamma LPJ, partial AL, partial XN over here. That's an N. So this term will cancel with this term over here, and now we're in good shape over here. So now we have the final results, and so our final result is that if we do this procedure over here, if we do the P derivative, N derivative minus the N derivative, the P derivative of AJ, what do we get? We get d by dx n gamma L P J, and then AL, of course, AL, and then minus d by dx P gamma L N J A L. And then what terms persist over here? Then we have the positive over here. So I have positive gamma N L A, and then what? And then we have a gamma L P J. And then over here, of course, this is an A, and then we have a minus gamma of what? Of N J L gamma A P L A. And now all I need to do is replace the A's with L's over here. So now we're going to do is we're just going to switch the A's with L's. So I'm going to change this A over here into an L, that L into an A, that L into an A, and that A into an L. That L and A are going to turn into A's, and that A is going to turn into an L. That A is going to turn into an L. Now all of them have ALs. And so we get this expression over here, that this expression is exactly equal to what? Is exactly equal to partial n, partial xn of gamma L pj, and then minus partial p of what? Of gamma n, of gamma L and j. And then plus gamma of what? Gamma of Na, L, gamma of A, Pj. And then minus gamma of what? Pa, Pal, gamma of A and J. Al. Beautiful. So after that laborious calculation, we arrive at this quantity over here, and this expression is true for any tensor. So by quotient law, this thing inside parentheses over here has to be a tensor itself. And that's what we call our Riemann curvature tensor, right? So this is going to be, so I could claim that this R, L, and then J, N, P, which is d by dxn of gamma L, P, J, minus d by dxp of gamma L, N, J, plus gamma N, A, L, gamma A, P, J, and then minus gamma P, A, L, gamma A, N, J is a tensor. I usually put a dot here in a period just so that L's upstairs. And this tensor over here is called the Riemann curvature tensor. So this thing over here is the Riemann curvature tensor. And you might see in some books, people will say, like, I can easily take this L index over here and lower it by hitting this with GLR. Which one? A lot of time I use that. If I hit this with G, for example, if we did GLM, right? So if I did GLM of RLJNP, that would be RM, J, and P, and sometimes people call this all four covariant tensor, the Riemann curvature tensor. It doesn't really matter because I can easily raise that index over there that corresponds to tracing over the covariant index and move it up to that, either move it up or move it down. Oftentimes it's useful to use this formulation because you have this nice sort of structure with the product of the Christoffel symbols over here, and it allows me to symmetrize when we're doing the Ricci tensor in a much easier fashion, right? So oftentimes, for example, when I trace over L and N, we're going to see in further videos that tracing over L and N over here is going to correspond either to the Ricci tensor or the negative of the Ricci tensor, depending on your convention, right? So I want to choose I have to think about this to make sure I get the sign right, but I want to choose the contraction over here to make sure that I have that the Ricci tensor of a sphere has something called is basically a constant multiple of the tensor, of the metric tensor itself, and that idea comes from the idea of like Einstein tensor. So we're going to really focus in on properties of this Riemannian curvature tensor and try to figure out how, after two contractions of this thing, we get something called the Riemannian curvature, and we're going to figure out how that scalar curvature plays a role in understanding of the structure of manifolds. Thank you very much.